Okay, do you see my screen?
Yes, sir.
Okay, good. Okay, so let us try to solve some 5-6 problems today. Okay, so this is our first exercise. So we have seen that the set of all strings, let's say over the binary alphabet 0, 1, thus that the kth last position is a 1. This DFA must have at least 2 power k states, and we can actually design a DFA with 2 power k states exactly, and therefore that is the minimal DFA. But instead of having 1 in the kth last position, I am happy if any of the last k positions in W has at least 1. Okay. And if W does not have so many positions, if it's a small string, if it is of length L, then the last L positions, which is basically all the positions, should have at least 1. So is the language clear? The last k positions, if the string has less than k positions, then I will count those many positions. And there must be at least 1. Okay. It is obvious that if you remember the last k symbols read, then you can design a DFA for this. But that will require 2 power k states. Okay. Here I want to show that 2 power k is too big. In fact, only k plus 1 states suffice. So in the first part, you prove that any DFA accepting this language must have at least k plus 1 states. And in part B, you show that these many states are good enough. Okay, so give me a suggestion for part A.
So we can make a DFA such that all the last k positions have 0, and then we can take note of that DFA.
Then do you think this is a very solid proof? Okay, we will design the DFA in part B. Let us do some reasoning for part A.
Okay. So if we design a DFA and then we minimize it, and then if it has k plus 1 states, then isn't that sufficient to prove part A?
Actually, we will see that part A and part B are essentially the same. Yeah, you can do that. And if you somehow prove that that's a minimal DFA with k plus 1 states, then also part A is proved. That's true.
Sir, we can consider the strings epsilon 1, 1, 1, 1, 1, 1 up to k minus 1 ones, and if there were less than or equal to key states, then for at least one string we would have a collision. That is for at least one pair of strings, we would have the two strings reach the same
Okay.
node in the DFA.
Yeah, some such proof. Yeah. So suggestion is I will consider the strings. Epsilon is not accepted. Okay, so part A. Suppose that a DFA with less than equal to k states accepts AK. Okay. Now, AK is not the entire sigma star, right? Therefore, it must have at least one non-final state. Okay. So I can say that this DFA must have at most k minus 1 final states. Because it will have to have at least one non-final state. Okay. So now if I consider these strings 1, 1, 1, 1, 1, 1, and up to, so 1, 1 square, 1 cube, up to 1 power k. They must all be accepted.
Yes, sir.
Okay. But this is, I think this is not a good example. This will not produce any contradiction.
Sir, if so there must be two strings that are accepted with the same state, and then we can assume that it's 1 power I and 1 power j, and then we can append key I zeros, I minus j zeros.
That will not produce any contradiction.
Okay, sir, that won't change the suffix. Yes, sir.
Yes, that will not produce a contradiction. So this is not a good set to start with. Something little better? Can you suggest?
Sir, 1 0 1 0 0.
Okay,
1.
That is better, right? So let us start with not this. So maybe 1, 1 0, 1 0 0 to 1 0 0 0, all zeros. Okay, so this length is k. Okay, so this is 1, 1 0, 1 0 square up to 1 0 power k minus 1. Okay. Now, this means that I will have, these are all accepted, and there are at most k minus 1 final steps, so there must be some repetition. So delta hat of s 1 0 power I must be equal to delta hat of s 1 0 power j for some I not equal to j, and let's say I less than j. Then append how many zeros?
k minus j.
K minus j or k minus 1 minus j maybe. Okay. Then what does this string become? 1, 0 power k minus 1, right? And this will become 0 power k minus 1 minus j plus I. Okay. Now j is less than I is less than j. Okay. So this is not in AK. This is in AK. But if I apply the delta hat, after reaching this, I apply to this. This is accepted. This is not accepted, and that immediately leads to a contradiction.
So why is the left one not accepted?
I minus j, if I write it this way, k minus 1 minus j. I think we made a mistake. I think we made a mistake. It should be
So we should add k minus I.
yeah, or you may do it this way. Let us take I greater than j. Yeah. So that j was not good thing. Okay. Now this is fine, right? Okay. So now this is fine. Yeah. This is plus I minus j. This is greater than equal to k minus 1 plus 1. Because I is greater than j. Okay. The problem with this inequality. Yeah. Now it's clear?
Yes, sir.
Yes, sir.
Okay. Okay, so that leads to a contradiction, and therefore we cannot have a situation like this. Now, what does it say about the DFA? A minimal DFA with exactly k plus 1 states.
The strings 1, 1, 0, 1, 0, 0, etc. should be accepted in different states.
That is fine. This immediately follows from this proof. That still does not give a DFA. Anyway, that gives the idea that it suffices to remember when the last one was read. Right. Okay, so I will have states like this. Last one read. So I will number maybe something like this. The last symbol read was 1, so 0. Last time I read 1 is last symbol is 0, and before that I read 1, 2 up to k. So how many zeros you have read after reading the last one? So this k is essentially standing for greater than equal to k. So these are all final states, 0, 1, 2 up to k minus 1. Okay. So state I means last red part is 0, 1, sorry. One, 0 power I. Okay. So which will be the start state?
K.
K. If I read 0 here,
Stay in K.
stay in K. If I read 1 here,
Go to state 0.
0. What about K minus 1? If I read 0,
Okay.
K. If I read 1, once again I go here. Okay. So it's something like this. Zero, zero, zero. Okay. And from everywhere, I have this. Okay. Fine. And this is basically a minimal DF. It has to be. Okay. Good. So here is another language, similar type of stuff. The last K positions contain exactly 1, 1. Okay. Here I'm calling last K positions having at least 1, 1. But now W must contain exactly 1, 1. And then you do a similar thing. Try to minimize it. Okay. So let us leave this to you in a very similar fashion. As far as I remember, these many states are necessary and sufficient. Okay, so you figure out why. It's a very similar exercise, so I leave it to you. Definitely, any DFA for EK contains at least 2 power K states. This is false, but this is the lower bound. This is the bound. Lower bound, yeah. Okay, maybe this thing is a fairly straightforward exercise. So we are talking about minimal DFA, and we have seen if a language is given, the minimal DFA has to be unique up to isomorphism. But what about NFA? Minimal is, of course, with respect to the number of states.
Sir, can we make epsilon transitions from one start state to another?
You can use epsilon transitions, but let us say these NFA are not epsilon NFA.
Sir, we can take the language a to the power k for any k over the alphabet a comma b, and then the DFA would be just of 2 states, and in the NFA we can just avoid the loop in the sink, and it will give us a different NFA, and it can't be less than 2 states because it is not sigma star.
Okay, so what is your range for K?
Any natural number. So it's the set of strings containing only A's.
No, 0 A's are allowed or not?
Yes, empty string is accepted.
This string is accepted, means I can have this, right? This is the minimal DFA, this is the minimal NFA.
Okay, sir. Yes, sir. Yes.
So this is A star. So if I take A plus, that is A star. Now it does not accept the empty string and accept anything else. So it will have to have any machine, NFA or DFA or whatever, epsilon NFA, it will have to have at least 2 states. Okay. Must have 2 states. Because there is a string that is rejected. Then, can you design two NFA for A plus?
Sir, we can shift the loop from final state to initial state.
Okay.
And like that will work.
So we can have 2 things. We can have a loop here, or we can have a loop here. Okay. So these are both accepting A plus. This one is not a DFA actually, because the transition from A is not unique. This is actually a DFA. Anyway, both are NFA. By definition, DFA are also NFA. Okay. So a minimal NFA is not necessarily unique. So good. Okay. So this is a minimization algorithm. Shall we do it? Or shall we go to, maybe I leave it to you because it's a mechanical procedure. So you try it out. So how many? Anyway, if I draw this DFA, let us see what happens. So the states are 0, 1, 2, 3, 4. This is the start state and also the only final state. Okay. If 0 comes, 0 square plus 0, it will stay here. 1 comes, come here. In 1, what happens? If 0 comes, 1 square stays here. And if 1 comes, 1 square plus 1 is 2. What about 2? 2 square plus 0 is 4. 2 square plus 1 is 5. What about 3? 3 square plus 0 is 4, right? 3 square plus 1 is 0. And from 4, what do I have? 4 square is 16. 16 is 1. 1 plus 0 is 1. So if 0 comes, and if 1 comes, go to 2. 16, 17. Okay. And I want to minimize this DFA. Do you see any
2 and 3.
1 and 3.
2 and 3 and 1 and 4.
2 and 3 and 1 and 4. So we would do this. Okay. Yeah. the quadratic residues and all that stuff. Anyway, 0, 1, 2, 3, 4. So,
So 3 is unreachable? So isn't 3 unreachable?
3 unreachable.
3, sir.
I cannot reach 3, right?
Yes, sir.
Oh, okay. In that case, throw this 3. Of course, I assume that this DFA is correctly drawn. So then forget 3. Unreachable. I do this construction on 1, 2, 0, 1, 2, 4. Okay, so that actually simplifies it. This is unreachable. So what should be your initial marking?
Two and 0, 2, 0, 4.
Okay. This is your initial marking. Then I will see whether 1 and 2 are equivalent. I mean non-equivalent. 1 and 2. Upon reading 1, this goes to this. Upon reading 1, this goes to this. 0, 2 is already marked. So they are not equivalent. What about 1 and 4? 1, 4. I cannot mark it, right? For the moment. What about 2 and 4?
We can mark it.
We can mark because upon reading 1, it comes here, which is already marked. I mean final. Upon reading 0, it will come here. So I can mark it. Okay. And I will not be able to mark this. So 1 and 4 are equivalent. Yeah, you can see that clearly. Anyway, so 1 and 4 are equivalent. Very small example, this one. Anyway, 3 you can throw because it is unreachable, and you can collapse state 1 and state 4. Okay. Anyway. Okay, so now let us do something on the Mayo-Hinle-Rod part. I hope I can cover a couple of things. So consider the regular language, A star, B star, B star is plus B star A star over AB. First, design a minimal DFA, and from this, identify the equivalence classes of this. So epsilon is there in the language or not?
Yes, it is.
Okay. So the start state will be a final state. Then if you read A, you are coming here. If you read B, you are going to accept strings only of the form B plus A star. Okay. So if I read A, I come here and it still accept. You may read as many as you want here. Likewise, if I read B, B. Okay. Then if a B comes, I am still going to accept so long as B's keep on coming. And if I read A here, I still keep on accepting as long as A comes. But if a B comes here, sorry, if an A comes here, or if a B comes here, I will enter a non-final state. Okay. So this is the DFA. Why is it minimal?
Cannot find any equivalent state.
Okay. So of course, this and this cannot be equivalent to any of this. So for each pair of this 1, 2, 3, 4, 5 accepting states or final states, I have to show they are non-equivalent. So for example, if I consider this and this, why they are non-equivalent?
Reading a B after that would result in a final state from the above state and not a final state from the below state.
Okay. So this way you can actually show, considering all these 5 choose 2 pairs, these are all non-equivalent. Okay. Maybe why this and this non-equivalent?
Sir, which ones?
Maybe this one, the start state, and this state. This one and this one.
Sir, reading A,
Upon
B.
reading A, we will
A.
go to non-equivalent states.
AB is still accepted, but if I come here, AB is not accepted. Okay, so this way you can prove they're all non-equivalent states, and this is a minimal DFA. How does it? What does it say about this partitioning?
It must be partitioned into exactly 6 parts.
Okay, 6 parts, and what are these parts?
Epsilon.
Epsilon is one part that is associated with this state, right? The partitioning is this one is associated with epsilon. This one
A plus.
A plus. This guy
A plus B plus.
A plus B plus. This one is B plus. This one is B plus A plus. And this guy, anything else, right?
Sigma star minus all of.
This is basically the complement of L. Okay. So this is the coarsest possible partition corresponding to this language L. Happy?
Yes, sir.
Good. Okay. Okay. So we have proved it using 2 ways. One, by pumping lemma. If k is the pumping lemma constant, we can anyway take a power k, big power k. We can also intersect this with a star b star That will give you the language a power k b power k. But now, can you use Maillard theorem to prove that this is not regular?
So we take the strings a power k where k is greater than or equal to 1, and then we want to show that there are an infinitely many equivalence classes.
Okay,
For the
so
sake
you
of
show that basically to show that this is not of finite index. Okay, so suggestion is a power 0, a power 1, a power 2, blah, 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 all belong to distinct equivalence classes. Okay, why? Because if I take a power I, b power, a power I and a power j for I not equal to j, okay. A power I, b power I is in this language, but a power I, sorry, a power j, b power I is not in the language. Okay. Therefore, there are infinitely many equivalence classes. Okay, although that is good enough for solving this exercise, can you identify the equivalence classes? Okay, so this exercise is solved. Fine, no problem. There is no problem in considering this fact. This is not a finite index, and therefore this cannot be regular. So as an additional thing, identify the equivalence classes.
So number of A's minus number of B's are same. That means they are in the same equivalence class.
Okay. That's it, right? So they are characterized by, let us do something like this. S of x surplus of A over B. Okay. So this can take value 0, plus minus 1, plus minus 2, plus minus 3, and so on. And this surplus of A over B uniquely identifies an equivalence class. Agree?
Sir, can you please repeat the last statement?
How many A's are there in X? Minus how many B's are there in X? Okay, that is called surplus of A over B in X. This can be 0, 1, minus 1, 2, minus 2, 3, minus 3, and so on. Okay. So each equivalence class consists of all strings of the same surplus. Agree or not?
Yes, sir.
Okay. So that's it. Okay, maybe another small question of the similar form. In this case, not saying Yeah, this is 0, but I just say it's a multiple of 5, this surplus. And this is regular. Of course, you can draw a DFA to prove that it is regular. Okay. But if I ask you to use the Miles-Neuron theorem, what does it mean?
Sir, we can show that there are only 5 equivalence classes.
Okay.
Surplus mod 5.
So if I call this language L to show that this has a finite index. Okay, so you need to identify the equivalence classes. What are the equivalence classes?
Surplus mod 5.
Surplus mod 5. Okay. So it's basically equivalence class. X goes to surplus of X mod 5. So this is in the range 0, 1, 2, 3, 4. Okay. So why?
Sir, any two strings having the same surplus mod 5 would be equivalent.
Yeah, so that's what it says.
Sir, because for any other string that is appended to both of them, they must be accepted if it has 5 minus sx mod 5 number surplus and rejected otherwise.
Okay, so you take X and Y with the same surplus. Okay, so Sx is equal to Sy. Then for any Z, what is the surplus of Xz?
Surplus of x plus surplus of z.
Yeah, so this is actually an additive function. And this is same as this plus this. Okay. Therefore, for all Z, if this surplus is a multiple of 5, we accept it. If it is not a multiple of 5, it will be rejected. Therefore, by definition, these are the equivalence classes, right? Good. And you can draw a DFA. It's basically a cycle. Right? What will be the DFA? Maybe let's just draw it. So there will be 5, surplus 0, surplus 1, surplus 2, surplus 3, surplus 4. Multiple of 5 means surplus should be 0. That is also the start state. If A comes,
For anything, if A comes, we go one clockwise, and if B comes, we go one anti-clockwise.
okay. Incidentally, forgot to mention one thing. For B, it's just the other way around. In fact, I forgot to mention one thing. Okay, so this is fine. So this is basically an MN relation. Why is this the coarsest one? I had to show a little bit more. If Sx is equal to Sy, then it is fine for all Z, accepted Xz is in the language if and only if Yz is in the language. So what is missing?
Sir, for two strings coming from the different equivalence classes, they are not equivalent.
Are not equivalent. I have to show also that thing, right? In order to complete the proof. So Sx not equal to Sy implies. Okay, so how do you show it?
Sir, S of xz is not equal to S of yz. So if one is accepted, then the other should be rejected, and if one is rejected, then the other should be accepted.
No, yeah. So I have to construct one such Z, right? So take Z for example. A to the power 5 minus Sx. Yes or no? If I append this here, the surplus will be actually Sx may be negative, may be positive, so I have to do something.
So we do 5 minus Sx mod 5.
Yeah, something like that. Mod 5. Okay. Then this will be accepted. Whereas since surplus of Y is not same as this will be rejected. So they are not equivalent. Okay. Okay, so fine, let me stop here. And you think about this. Okay. Otherwise, we could cover almost everything that I planned. Okay, fine. So let us stop here. Yeah, if you have any immediate question, let us know. No questions? Okay.